Hello everyone, my name is Drake Gibson. I'm here to work through homework 2 with you today. Homework 2, we are given that a 10 centimeter long uniform cross-section capillary, initially containing pure liquid water and deuterium on its left and right sides respectively, and at t equals 0.1 seconds, the max molar diffusion flux J is equal to 2.78 moles per meter squared second. We're also given that the molecular weight of deuterium is 20 grams per mole. The density of deuterium is 1110 kilograms per meter cubed. The molecular water by definition is 18 grams per mole, and the density of water is 1000 kilograms per meter cubed. So the question 1 is asking what is the overall mass flux N corresponding to the max molar diffusion flux. So I want to start off by describing the capillary system, where we know that from 0 to 5 centimeters is pure liquid water, and from 5 to 10 centimeters is pure liquid deuterium at t equals 0 seconds. So we want to know what is the molar diffusion flux throughout, and we know that for a component, the molar flux of that component is equal to the molar diffusive flux of that component plus the mole fraction times the total molar flux. And we know in this case that the total molar flux is equal to the molar flux of one component plus the molar flux of the other component. And in this case, since it's a binary component or binary mixture, we know that the component A is equal to the negative of the component B, and this is because they are equally diffusing into each other at once the divider is released, and therefore allowed to diffuse evenly into each other. And therefore, we also know that the total molar flux is equal to 0 because this, once again, like the last homework, is a closed system, so therefore it is equal to 0. And so then we can take and get rid of this bulk component and say that this is equal to 0 because the total molar flux is equal to 0. And therefore we have that the molar flux for a component is equal to the molar diffusive flux of that component. And we also know that for a capillary system that the molar diffusive flux of the one component plus the molar diffusive flux of the other component is equal to 0. So therefore the molar diffusive flux of water is equal to the negative molar diffusive flux of deuterium. And in this case, we know that this max diffusive flux is 2.78 moles per meter squared second. So therefore, the molar diffusive flux of water is equal to 2.78, and deuterium is the opposite and negative 2.78 moles per meter squared second. So now we want to get the molar diffusive flux into a mass diffusive flux, or a mass flux. So the way we can do this is we can take the molar diffusive flux of water times the molecular weight of water in order to get the mass flux of water. So if we plug in our numbers that we were given, we have the molar diffusive flux is 2.78 moles per meter squared second times the molecular weight of water is 18 grams per mole, and therefore that gives, these cancel out the moles, and you're left with grams per meter squared second, which is your mass flux. So you're left with 50.04 grams per meter squared second is your mass flux of water. And you're going to follow that same procedure for deuterium over here, and you have your negative 2.78 because once again that's equal and opposite to the molar diffusive flux of water times the molecular weight of deuterium, and you end up getting negative 55.6 grams per meter squared second. So then we know by definition that the total mass flux is equal to the mass fluxes of each component, and in this case we have water and deuterium. So you plug these numbers into this equation, and you get the total mass flux is equal to 50.04 grams per meter squared second minus the 55.6 grams per meter squared second. And therefore, you are left with negative 5.56 grams per meter squared second. And just based on what we've done in the past, if you convert that to kilograms per meter squared second, you're just dividing by 1,000, and you get negative 5.56 times 10 to the negative third kilograms per meter squared second. Now for question 2, which is make an order of magnitude estimate for the maximum driving force for diffusion at t equals 0.1 seconds. For some background, the driving force is relatively the strength of diffusion of one component into the other. And by definition, this driving force, in this case d subcomponent I, is equal to the sum of j equals 1 to n of the mole fraction of the one component times the molar diffusion flux of the other component minus the inverse, in this case the molar fraction of the component j times the molar diffusion flux of component I. And this is then divided by the total concentration of the solution times the Stefan-Maxwell coefficient, diffusivity coefficient, Ij. So if we go ahead and plug in what we know, so we're going to use 1 as water and 2 as deuterium in this case. So by definition we have the sum here, but if we were to put in j equals 1 and I equals 1, then these would equal 0 and therefore equals 0. So we're just going to focus on when it's the second term. So therefore we plug in, we have the molar fraction of 1 times the molar diffusion flux of 2 minus the mole fraction of 2 times the molar diffusive flux of 1 all over the concentration times the Stefan-Maxwell coefficient. And to simplify this equation a little bit further, we know that the mole fraction of any component in this case, but we're going to say 2, is equal to the total 1 minus the molar fraction of the other component. So in this case, we have the molar fraction of 2 is equal to the 1 minus the molar fraction of 1. And we also know that the molar diffusive fluxes have to sum up to 0. So therefore, the molar diffusive flux of 2 is equal to the negative molar diffusive flux of 1. So if we plug all of this into this equation and simplify here, we end up getting the negative molar diffusive flux of 1 divided by the molar concentration times the Stefan-Maxwell diffusivity coefficient of 1 to 2. So if we look back at what we know that the max molar diffusive flux, or in this case the molar diffusive flux of water, is equal to 2.78 moles per meter squared second. And for liquids, a order of magnitude estimation is about equal to 10 to the negative 9th meter squared per second. So we're going to use that as an estimate. And then if we want to calculate the molar concentration, we use the densities divided by the molecular weights and then divide it by 2 since there's 2 liquids in this case, and we end up getting 55,528 moles per meter cubed. And so what we want to do here is plug all of these knowns into our equation that we derived here, I guess in this case here. So we have the driving force of component 1, or water in this case, is equal to 2.78 divided by 55,528 times 10 to the negative 9th, and what we get is 50,065 meters to the negative first, or 1 over meters. So a general order of magnitude guess estimate for the maximum driving force for diffusion at t equals 0.1 seconds is about 10 to the 4th. You can just figure that out from here for the max driving force. Finally, I'm going to walk through the graphs we were given. For the density charts, we know that initially that there is the divider at 5 centimeters, and on the left is going to be, so from 0 to 5 centimeters is pure water, and on the right side from 5 to 10 centimeters is going to be pure deuterium, and a much more like steep slope between, because there is not any deuterium on the left side and no water on the right side initially. Then as things are allowed to mix, we have a much more gradual change in density from the left to right side of the capillary. And finally, it's going to reach equilibrium, so there's going to be deuterium throughout the entire capillary and water throughout the entire capillary. Similarly, for the concentration of water and deuterium, you have that steep slope at the beginning because you have pure water on the left and pure deuterium on the right, with a much more gradual change in concentration as things are allowed to mix and move throughout the capillary. And then finally at equilibrium, the concentration is going to be equal throughout the entire capillary system. Then we have the, sorry, I don't know if you can see this. There we go. The molar diffusion flux is going to be a very steep change once that divider is changed, and we know that the max diffusion flux in this case is 2.78 moles per meter squared second, and opposite for equal and opposite for the deuterium. So in this case, negative 2.78 meters or moles per meter squared second. And as things are going to mix and intermediate step, there's going to be a much more gradual slope of the diffusion throughout, and that's reflected here with the water and deuterium. And then eventually there's going to be no diffusion throughout the capillary because it's reached equilibrium. So therefore, component 1 isn't going into component 2, and component 2 isn't going into component 1. So therefore, the molar diffusion flux is 0 throughout the entire capillary. And finally, the total mass flux throughout the capillary. So initially, you have that divider, and we calculated in step 1 what the max mass flux would be, and that's about negative 5. So that's going to be a very steep slope to that point in the middle where the mass flux is the highest. And then as you go throughout in the intermediate, there's going to be a very gradual slope of the mass flux throughout the tube. And then finally, you're going to have no mass flux throughout the entire capillary because, like I said, there's no diffusion or no flux movement between component 1 into 2 or 2 into 1. Thanks for listening, and that is all for my homework 2.